Welcome to the third course of the Gravitational-Wave School. On behalf of all of us, I am happy to welcome Keith Riles to give this particular course. Keith did his PhD from Stanford in elementary particle physics, and his current research interests involve both gravitational waves and elementary particle physics. He has been a part of the LIGO scientific collaboration from a long time and has sort of had a lot of leadership positions in this particular collaboration. He has been involved in continuous search for continuous gravitational waves for a long time, and also currently interested in the science case for the linear collider. This particular course is about rapidly spinning neutron stars and the emission mechanisms which we encounter when dealing with them. With that.
Yeah. Thank you, Bala. Can you hear me in the back? Great, thank you. Well, good morning. It's good to be here. Thank you for coming, and thank you to the organizers, Bala and Prayush and Ajith, for inviting me. Wonderful campus here. I'm enjoying being here. It's my first time in India, and the weather is a little more temperate than I expected. It's actually been quite pleasant. Very happy about that. So, without further ado, let me write down the title of this set of lectures. And you'll notice there's a notable omission. So the official title that I was given by the organizers was Rapidly Spinning Neutron Stars. Oh, I just remembered, I'm not supposed to write that high. All right, let me try again. So, rapidly spinning neutron stars. And emission mechanisms. Now, what's missing from this title is an adjective that you might have expected: gravitational wave emission mechanisms. Now, I'm taking that as a license to talk about other emission mechanisms, electromagnetic emissions, in addition to gravitational wave emissions, not just because I think that's an interesting subject in and of itself, but also because much of what we know empirically about neutron stars comes from the electromagnetic radiation that we detect from these very exotic beasts. So let me outline. So let's leave this here for now. Let me outline briefly the lecture topics. And once again, I forgot, I'm not supposed to write that high. The lecture topics this week. So just some broad brush. I just want to give you some sense of where we're going. So today, we're going to start with a brief review of the very basics of neutron star physics. Now, I do so knowing that you just had a week of lectures concerning neutron stars, and so there's going to be some repetition here, unavoidably. I hope you'll forgive me for that. That's in part because I want to make sure we're on the same page, that we're coming at this from the same framework, and I'm making the same basic assumptions that you're already familiar with, and in part because if you're like me, repetition helps in learning. So hopefully you'll look at this and say, oh yeah, I know that, I know that. Good. If not, then maybe you've learned something new. Now, one thing I'm going to focus on, I don't know how much coverage this got last week, but rotational effects are very important for this topic that concerns rapidly spinning neutron stars. We need them to be rapidly spinning in order to detect them gravitationally with current ground-based interferometers. Magnetic fields, as you learned last week, are very important to understanding pulsars in particular, but neutron stars in general. And I'm going to spend a fair amount of time talking about the known pulsar population. As I said, much of what we know from electromagnetic radiation, and that's dominated by what we've learned from pulsars. And so we'll talk about what creates those pulsations, what we think creates those pulsations, although it's not rock solid how that works. And then I'll start getting into the topic of gravitational wave emission. I'll start with some very basics, again, just to make sure we're all on the same page. And then I'll focus in on continuous gravitational wave emission. And I'll address some of the likely causes, we hope, of that kind of emission. And those include mountains. And I should really put mountains in quotation marks for a couple of reasons. One is that the mountains are not very high, even in the best case scenario, and also because they don't really look like mountains. As you'll see, these are more like vast bulges on the surface of the star. It's more likely than well-localized mountains. I'll talk a bit about buried, I don't know how long it's going to take me to learn this. I should write below this line. I'll talk about buried magnetic fields, which could actually be very important for understanding what may be our best scenario for the first detection of continuous gravitational waves. So that deserves a bit of coverage. I'll talk about another kind of emission that's different from the quadrupole mass emission that we tend to focus on normally. Our modes, which is a quadrupole current emission, is something that may again be one of those promising ways of getting our first detection. I'll also talk about accreting systems. And there are arguments that an accreting system is our best chance for the first continuous wave detection. We really don't know. One of the things that, well, I think you'll learn this from Alicia, is that we really don't know what our most promising target is for the first detection of continuous gravitational waves. So we look for a lot of different possibilities. Now, toward the end of the week, I'm going to talk about quasi-continuous wave scenarios. And among those are pulsar glitches that we think of as being, quote, transient CW sources, because they, in one scenario anyway, they turn on and then they gradually die away. So they're not as continuous as what we normally think of as continuous gravitational waves. I'll also talk about a more extreme case of a post-merger remnant, which in some cases may be what are called millisecond magnetars, extremely high frequency and high magnetic field objects that may be promising sources. And then at the very end of the week, I'm going to talk about what I call lamppost physics. And I'll explain what I mean by that when we get there, if we get there. And I should say that I have not presented this sort of material at the blackboard in the past. I've typically given slides, and I don't yet know how well my pacing will be. So if I suddenly start slowing down dramatically or speeding up dramatically, you'll know that I misjudge things when I put together the talks. But anyway, if there's time at the end of the week, then we'll talk about these lamppost topics. Okay, so with that introduction out of the way, let me dive into neutron stars. And again, this is material that will be very familiar to you from what you learned last week and probably what you've known previously to that. And I don't want to repeat a lot of what you've already learned, but again, the repetition may be helpful to you. So, basics, these things are born in the core collapse of massive progenitor stars. And I'm going to use a canonical range and say that that's in the ballpark of 8 to 30 solar masses for that progenitor before collapse. And you'll see different ranges quoted in the literature, but that's reasonably close to the nominal. So we think that there's an iron core prior to this collapse that is surrounded by other layers, one or more layers of other elements, such as silicon, for example. And this grows massive enough on its own, the core, that it becomes unstable. And of course, one possible way to get that kind of instability is through electron capture, where electrons bind together with protons to create a neutron and emit a neutrino. And in any case, you end up losing an enormous number of electrons and losing that electron gas degeneracy. And the star, thanks to the famous Chandrasekhar instability, the star collapses. And when it collapses, it does so quite suddenly. It does so more or less in free fall. And all that material just comes crashing down until it reaches nuclear densities, at which point we expect a bounce takes place. And so at that point, we have what's sometimes called a proto-neutron star. Which has a radius in the ballpark of 10 kilometers. We expect in that process that a supernova occurs. And that supernova, from the bounce, includes a vast amount of neutrino emission, which then itself blows up the envelope of the material around it. So that's the sort of the standard model, conventional model of neutron star formation. And what you end up with is a final star that has a mass in the ballpark of 1.4 solar masses. And its structure is not well understood. And putting that in quotation marks, because it's really a euphemism for saying it's poorly understood. I'll be using that phrase a number of times this week to describe various phenomena, our understanding of phenomena. So when we say not well understood, that usually means that we have a vague notion of how it might work. We have quantitative calculations under certain particular models, but we don't know which models are correct. So we just do the best we can. As you'll see in some of your exercises, in some cases it doesn't make that much difference what you assume. In other cases, it very much makes a difference what you assume. Okay. So let me talk a little bit about equation of state. I believe you covered some of that last week. I didn't see the lecture, so I don't know in how much detail you covered this topic. But let me just, as I said, make sure we're on the same page. So first of all, the equation of state refers to a parametrized relation between pressure and density. And we usually make a low temperature approximation because the temperature of neutron stars that have any age to them at all typically is well below the Fermi energy for the neutrons. And so it's not unusual to just ignore any potential temperature differences, temperature variations. Okay, now that equation of state may be smooth. For example, it might be a polytrope. And I think you discussed polytropes last week. So you might say that the pressure is proportional to the density raised to a power of 1 plus 1 over n. That's one way to parameterize the polytrope model. It may be that smooth, probably not. It may have, instead, some sharp transitions. It may have sharp phase transitions. And in fact, the current literature argues that there's quite a number of papers out now arguing that we have evidence now that there is something sharp happening internally. The choice of the equation of state governs the mass-radius relationship for a star. Via the famous TOV equations, the Tolman, Oppenheimer, Volkoff, equations, which I'll just call TOV for short. And we write that equation down over here. So we say the PDR, as we imagine going out from the center of the star to higher radii, dPdR equals minus G over R squared times M of R, by which we mean the mass inside of that radius, plus 4 pi R cubed pressure at that radius R over C squared. By the way, I'm going to use SI units throughout these lectures. I prefer SI units, even though it means carrying around extra constants, because it's easier to check myself. And then we have this famous denominator. It also depends on M of R. and leads to all sorts of interesting phenomena. Oops, r c squared. Okay. So explicitly, m of r is the total mass inside of radius r. And the differential equation that governs its value in any given radius r is dm dr is 4 pi r squared times this density. And as you probably know from last week, this is the total mass, including baryon mass plus any negative effects due to gravitational attraction. Now, in the Newtonian limit, one can neglect the pressure, say that P of R is much less than rho of R times c squared. And in that limit, one gets a relation, GOV equation, dP dr is approximately minus g m of R rho of R over R squared. And so in that Newtonian picture, which I like to keep in mind, the sanity check, each mass shell that we add to the star at a given radius r and let's imagine that this shell has a thickness dr, is then attracted with a Newtonian force what is called dF in magnitude that's approximately minus gm of r over r squared times rho of r 4 pi r squared dr. And of course, this is dm of r. So this makes sense. Okay. Again, I think you covered this last week, so I don't want to belabor it, but make sure we're on the same page. Okay, and then in this kind of equation of state approach, one starts from some assumed central density at the core of the star, rho where r is equal to 0, and you integrate out until you reach a point where the pressure has gone to 0. Namely, you're at the surface. And so that's in some sense an empirical way, using whatever your assumed equation of state is, and it's an empirical way to determine what the mass of the star is for an assumed central density. And so one can try different central densities. Yeah. Oh, I can't go this far? Oh, okay. Is this the edge here? Oh, really? Okay. Okay. So let me start back on the left then. It is marvelous to have so much blackboard space. It's okay to start here. It is okay. Okay, so the idea is you try different central densities rho of r equals 0. You just try them and empirically find through numerical integration of your assumed equation of state where you end up in terms of radius. And that allows you to empirically, in the sense of numerical integration, map out the mass-radius relation I alluded to earlier for that assumed equation of state. So let me just sketch that. So horizontally, I have the radius in kilometers, and vertically, I have the mass in units of the solar mass. And I'll put one tick here at 1 solar mass and another one here at 2 solar masses. And here I've got 5 kilometers, 10 kilometers, and I'll put in a 15-kilometer tick mark. And just very crudely speaking, we can classify this mass-radius relation as being soft or hard depending on where we end up. So imagine that we start here with one equation of state and end up here not much higher than 1 solar mass. This would correspond to what's known as a soft equation of state. And then a different equation of state might end us up here, up above 2 solar masses. And I didn't draw this very accurately, but these curves stop when they start to turn over, because that's the point of instability. You've reached a point where if you add more mass, the star actually shrinks, and that's a runaway process, so that you end up with a black hole. So these endpoints correspond to the maximum mass at the point of instability, namely where dmdr is equal to 0. Okay, so that's a crude diagram. If we now bring up the first slide, we can look at a more precise set of curves. I don't know if that's something I can do, or screen has switched to the blackboard. Let me try clicking this. There we go. Okay, is that showing up? Yeah. Okay, thank you. Okay, so here are much more precise curves, equation state. You probably looked at something like this last week. I don't know if it was the same diagram, but it shows you a whole bunch of different possibilities. And this reinforces what I said earlier about how things are not well understood. Really means they're not well understood at all, because until recently, virtually all of these different curves were still in play. Now, some of them have been eliminated, as we'll discuss in a moment, but these various curves that go up high correspond to hard equations of state. Those are different nucleon models, where you end up with nucleons interacting with each other, 2-body, 3-body, and so on. And then some of the softer equations of state correspond to, for example, strange quark matter in green, or these nucleon plus exotics, phase transitions in pink. They tend to end up with lower values. One key point to realize is that sometimes just making a single empirical measurement can be quite illuminating. And you can see that from this diagram, in that there are some measured neutron star masses that are quite high that are completely inconsistent with some of the more extreme soft equations of state. And I should say that we have to rely on these kinds of measurements astronomically to answer these sort of questions, because these particular densities and temperatures are just not accessible to us in the laboratory. We're just in a completely different realm in a cold neutron star. So ideally, what you'd like to have is a simultaneous measure for a single object of both the mass and the radius, and that very quickly eliminates some EOSs. Unfortunately, that's a really hard thing to get, primarily because of the challenge of measuring the radius of a neutron star, which we can't do directly. We have to use indirect ways. The mass is more straightforward in some binary systems. But if you look at that diagram, even the mass alone is very informative. So we have one star, J16142230, the one on the top there, at 2 solar masses, that is just way above some of those equations of state. So a well-measured high mass alone helps. Another potential piece of information that would also be extremely helpful would be gravitational wave tidal effects in binary neutron star mergers. So in the final moments of a merger, one expects the star to be, both stars to be ripped apart in some sense. And in that process, one learns something about the equation of state, at least for the outer layers of that star. Unfortunately, so far, what we've learned about is the lack thereof of these tidal effects, because our detectors so far are not quite sensitive enough to measure tidal effects. But the fact that they have not been measured is also useful information, because that disfavors some of the more extreme, very large radius stars that really should have shown some measurable effects. Let me talk a little bit about the structure of neutron stars. So I'll draw a crude diagram here. So here's my star, and imagine I have a pie slice. And I'm going to expand the pie slice and just show you very crudely what that looks like. So in this model, we have an inner core. It goes out to roughly half the radius of the star. A lot of uncertainty about exactly how far it goes out. And then we have the outer core, which goes most of the way out to the rest of the star. And then we have a crust, and it's conventional to divide the crust into an inner crust and an outer crust. And even this is not really to scale. It'd be hard to see the outer crust if I do it to scale. So let me just say a few words about each one of these layers. So our outer crust is of order 100 meters thick. And we think that that is mostly made up of a lattice of neutron-rich nuclei. And then we move into the inner crust, where the density rapidly increases. And the inner crust, again, we don't really know these numbers very well, but it's in the ballpark of 1 kilometer thick. And we think that in this regime, we have superfluid neutrons, which are extremely cold. And we also have something called vortex pinning, which I'll talk about a good bit later on in the week. We have vortices of angular momentum from the superfluid neutrons. The outer core, which is of order 3 to 4 kilometers thick, has not only superfluid neutrons, but also has a lot of superconducting vortices, the ones that tend to get pinned in the inner crust. And then we come to the inner core, and that's where one has the epitome of something that's not well understood. So somewhere in the ballpark of 5 to 6 kilometers thick. And what's in there is not at all clear. Hyperons are a reasonable guess. These densities, we don't know for sure. It's possible that instead one has deconfined quarks, really aren't assigned to any particular hadron. And there are some theorists who favor a QCD analog to superconductivity called color superconductivity. So there's a lot of uncertainty in that inner core, and there's actually a lot of uncertainty in the outer layers also. But what we're most concerned about this week is what's happening generates gravitational waves. And for gravitational wave emission, particularly continuous gravitational wave emission, we think that what's happening in the outer layers is probably most relevant. So the crust and also the crust transition to the core, and that transition region is sometimes called the mantle, in analogy to the Earth's mantle. That is probably most relevant to continuous gravitational wave emission. I should say, though, that that's not known for sure. There is the intriguing possibility of an exotic alternative in which the core plays a role. One might have a solid strange core. I wouldn't bet on it, but it's the kind of thing we can look for in principle. Okay, I guess I'm ready. You may have just transitioned back to the blackboard on the screen. I'm ready for the next slide. I wasn't paying close attention to what was done back here earlier. Yeah, I don't want to touch that. I see, it's a Zoom session. Okay, great, thank you. Okay, so this is a diagram taken from an article by Newton that illustrates possibly what's happening in the transition region I alluded to. So again, we have a conventional model of these different layers and hypothetical densities associated with each layer. I just want to point out that in this region where you go from the outer crust into the core, we have this possibility of nuclear pasta, where we go from more or less pure neutron superfluid with occasional heavy nuclei, neutron-rich nuclei, to vast agglomerations of those neutrons into spaghetti-looking things and lasagna-looking things. And eventually, you become completely dominated by this neutron-proton fluid. The reason I wanted to highlight this is something I'll be getting back to later on in the week, where what's happening here may affect potentials for gravitational wave emission. And it also affects possibly, in fact, one of the points of this article was that this may be affecting the magnetic fields that tend to die off sooner than you might otherwise expect in older neutron stars. This could be a source of ohmic dissipation, all of the disorder that occurs at this boundary. I'll talk a little bit about that later on in the week. Okay, let's see what the view choices are. Well, I was hoping this would be straightforward, but I'm not sure I know how to get that blackboard back up again. I assume you wanted to have the blackboard up. I'm done with that diagram. Have the blackboard be visible on the screen again. Assume that's the preferred. I'm done with that diagram. Yeah, you just leave it there. Okay, thank you. Okay, so let me talk now about rotational effects. Forgot where I left off on the ended there. Let me talk about rotational effects for these rapidly spinning neutron stars. So one key point to keep in mind is that if the rotation is too fast for a given neutron star, that there will naturally be mass shedding at the surface. The matter at the surface literally flies off if you try to spin a star up too fast. So to understand that, at least semi-quantitatively, let's assume a very simple model. So our starting model is to assume a uniform, rigid, spherical star with a gravitational mass, m, and an outer radius, r. Okay, so again, let's just use Newtonian mechanics. So according to Mr. Newton, this test mass at the surface is about to be shed when the centripetal force required to keep it on that surface, mv squared over r, is equal to gm small m over r squared. Just keep going in that circle. With v equal to omega times r. And I'll usually use capital omega to refer to the rotation frequency of the star, the angular frequency. As I said, we're assuming a uniform solid sphere model for simplicity for the moment. And so with this uniform density, m is given by 4 pi over 3 times what I'll call rho naught, being a constant, times the radius cubed. And so if I take as specific numbers the mass equal to 1.4 solar masses, and I'll take the radius of the star to be 12 kilometers, which seems to be about right based on current measurements, a variety of realms. One gets rho naught in the ballpark of 4 times 10 to the 14 grams per centimeter cubed, which is well above nuclear densities. So as you know, these are very dense objects. And so if you take this very simple model where we have this constraint, which you can think of as Kepler's third law constraint, then we end up with a shedding frequency given by the shedding angular velocity over 2 pi that is in the ballpark of 1700 hertz times whatever the true density is over rho naught raised to the 1/2 power. Okay, so it's a very high frequency. We don't know of any neutron stars that spin anywhere near that high, although they do go fast. So that's one benchmark. In reality, there's one significant effect that is, I won't say not well understood. We think we do understand it reasonably well. Most of the star is in some sense liquid. It is free to be deformed. And it actually does deform if a star is spinning really fast. It deforms a lot, okay, at such spins. And so, in fact, it's no longer legitimate to be using this spherical model, because if we have something that's liquidy, it's not going to remain a sphere when it's spun up that fast. And so you end up with a larger actual radius at the equator. is this board okay to write on? Yeah, okay. So in reality, I guess I could draw this diagram down here. So if we have omega equal to 0, and we have a sphere, it's not going to look very spherical when we are done spinning it up. So we're going to have a radius r for, say, the polar regions, and I'll have a radius plus an extra height for the equatorial region, where I'm spinning the star about a vertical axis like this, and I'm spinning it at close to the shedding frequency. So this deformation is actually can be quite substantial if you really push something to the limit. And so in a uniform liquid model, this is a model you'll be looking at in one of your exercises, this height is of order 1/2 of that polar radius. So I haven't actually exaggerated things very much in that diagram, if you really spin something up to the shedding frequency. So at breakup speed, where the star is no longer really sticking together, you have that kind of deformation, and that naturally is going to reduce the shedding frequency significantly. So you drop down to something like 900 hertz for a mass of 1.4 solar masses and a radius of 12 kilometers. Notice that there's a pretty strong dependence on that assumed radius. And in fact, if I were to change that radius to 10 kilometers, I would get a higher value of 1200 hertz. So it matters a great deal what the actual outer radius is at the equator. And you'll be filling in some of these steps in an exercise. Okay, now that was a Newtonian approach. There are some relativistic corrections which are non-negligible. I'll just summarize those here. And in fact, I'm going to just summarize what they are for a maximum mass star. And those calculations, and you can look in the Anderson text to see some of the details. That shedding frequency is more like 1100 hertz times this max mass over 1.4 solar masses. And again, we get this rather extreme dependence on R max, -3 halves. And so in this 1100 hertz is of order 1400 hertz if I shrink that radius down to 10 kilometers. And if we are in this realm where we are really pushing the limits on how fast we can spin the star, then we get what are known as supermassive stars. So let me talk a little bit about that. So we're looking at the extreme of pushing a star's mass as high as it will go at the same time that we're speeding it up as high as it will go. And so that describes what is, I'm going to call a supramassive star. Sometimes this is called a hypermassive star. Note that there is some There are differences in the literature about the nomenclature for these kinds of stars. Sometimes a distinction is made between a star that is supermassive, that is spinning, co-rotating like a solid body, versus one that's differentially rotating. If you're differentially rotating and the inner core is spinning faster than the outer core, then your mass shedding frequency can be considerably higher. So if you're in this realm, the star is actually sustained against collapse by the rotation itself. That is, if you let it spin down, the star becomes unstable. So that spin down leads to collapse. And we'll talk more about that later in the week. At this point, let me show another slide. Do it from here. Okay. So again, this is also from the Anderson text. This is showing a graph of the mass in units of solar mass versus the central density of a star. And the solid curve shows you what you have for a non-rotating star. So this would be a classic example of a TOV curve. And once it starts turning over, then you have instability and you get a collapse to a black hole. This region above the black curve that's shown in gray corresponds to these supermassive stars, where if you spin them up fast enough, then you can have a mass that is nominally above the limit. But eventually, as these stars spin down, they will drift over and they'll end up hitting a point of instability shown by this, or a line of instability shown by this dotted curve. So we don't know how important this is, but it could well be important in the realm of post-merger remnants, where we have a very massive and probably very rapidly spinning hyperneutron star that may well last for some period of time before it suddenly collapses. So this may actually have some bearing on the kinds of detections that are being made by LVK these days, although we haven't made a lot of binary neutron star detections lately. Okay, so those are extremes where we push the models to the limits and say, well, what's the most extreme case we could come up with? But what's more relevant to us when we're looking for continuous gravitational waves is what is plausible and reasonably common, not just what nature allows as an extreme. So what F is actually plausible? So the maximum need not be plausible. Okay, so let's kind of go back to the basics to try and understand what you would just naively expect for the spin frequency of a neutron star. Not what nature would allow you if you had full control over the creation of one, but what you might actually see in nature. So let's look at what happens at birth. And I'm going to somewhat arbitrarily use the closest star to us as an example. Even though we know, or we're pretty sure we know that our sun will never become a neutron star, it's not that far away from the mass of a neutron star. Let's pretend that it can collapse to a neutron star. So right now its radius is of order 700,000 kilometers. And its current rotation frequency is about once per 25 days. So it's a slow spinner. Now we can impose angular momentum conservation and say, well, what happens if we take that 700,000 kilometer radius star and we just crunch it down? Is it going to spin up the way of, say, a ballerina would? And the answer is yes. So we can apply angular momentum conservation to see how fast the star might end up spinning at the end. So our angular momentum L is I times omega. And I'm just going to use a very simple model here. I'll pretend the star is a uniform sphere. So my moment of inertia is 2/5 mr squared times omega. So this is just a uniform ball model. Obviously, that's not very accurate for the sun, but we're just trying to get a qualitative, intuitive feel for what's possible. And so if you apply that conservation notion to the before and the after angular momentum of this star, it starts off with that radius and that frequency, then our collapse to a radius that's in the ballpark of 10 kilometers gives a final frequency of about 2.3 kilohertz. So it's not outrageous to think that when you shrink a big star down to a small, tiny sphere of 10, 12 kilometers, that you're going to get something that's spinning pretty fast. As I said, I just chose arbitrarily the star that is closest to us, and look, it's already well above the shedding frequency. So it's not crazy to think that you might actually get something that at least initially could have a high spin rate. Of course, you can quibble about this uniform ball of mass model for the sun. Obviously, there's more density near the center than there is at the outer edges, but still, it was an arbitrary choice. Okay, now after the collapse, we don't expect even a very fast spinning star to remain fast spinning. Generally speaking, we expect a rapid spin down due to magnetic dipole emission at a minimum. And ideally, supplemented by gravitational wave emission if there's enough asymmetry in that star at its beginning. So if we're lucky, there could also be gravitational quadrupole emission. So if you have a very freshly born star, if, for example, a supernova, core collapse supernova were to happen in our own galaxy, in one of our observing runs, LBK observing runs, then we might well have something with a very interesting signal to it. Now, I'll talk more about that later in the week. But for now, let me just focus on the electromagnetic emission and comment a bit about what is actually observed in nature. as I said, these shedding frequencies I've been calculating or giving you summaries of are much higher than what has been observed, despite the fact that what has been observed is fast. So let me just remind you that the fastest known pulsar, which was discovered within the last 20 years or so, has a rotation frequency of 716 hertz. Now that's out of what are now about 3,600 known pulsars. So it's not a small sample of stars, and this is the upper limit for the time being. We think that the fastest stars, ones that are close to this value, really the ones that are within a factor of 5 of this value, are, or previously were, in accreting binary systems. And again, that's something I'll talk more about later in the week. We'll look at some reasonably promising targets. Okay, so let me come back to this point, that after a collapse, we expect a rapid spin down due to magnetic dipole emission in any case. Whether or not we have any significant gravitational wave emission, we do expect the magnetic dipole emission because we expect pretty strong magnetic fields in these stars. So let's talk about magnetic fields. So neutron stars have enormous magnetic fields, at least by Earth standards. So the range is roughly from 10 to the 8th up to 10 to the 15 Gauss. And that's just what we know about at the surface. It's possible that there are even stronger fields buried inside of the star. I'll discuss that a bit later on in the week. So how do we know that? How do we know that these fields are so strong? Well, there's more than one piece of evidence that points to these fields being strong. And then I'll talk about why it's not crazy to expect such strong fields. So the evidence primarily from cyclotron lines, spectral lines, and this is more model dependent, from the spin down that is observed if you make the assumption of magnetic dipole emission. Okay, so we have two pretty independent lines of evidence to suggest that we have very strong magnetic fields at the surfaces of neutron stars. And so a natural question is, how does it get so big? So how does B get that big? So once again, let's return to our familiar sun. So the sun has a magnetic field that's in the ballpark of 1 Gauss at what we would call its north pole. So the end of the spin axis that aligns most closely with our own north pole spin axis. The source of that magnetic field is unclear. Presumably there's some sort of dynamo happening inside. But for the sake of doing a calculation, we can try modeling it in the following simple way. Let's pretend that what we have in the sun is some rotating ball of charge, tiny subset of the total mass of the star, but some of it is charged and it's rotating. And let's just give it some density that I'll call rho sub q. So in this model, we have this rotating ball, angular velocity omega, and it has a total charge q that, again, this is not the whole sun, this is some subset of the sun of rotating charge. And let's imagine, as we did earlier, let's imagine crunching the sun down, forcing it to shrink its radius down to ballpark of 10 kilometers and asking, what is that going to give us? What's that going to do to the magnetic field? I should note that known pulsars have B fields that are misaligned with the spin axis. As they don't line up with the spin poles, which of course is also the case for the Earth, where our north magnetic pole doesn't line up with the north geographic pole. But let's set that aside. Let's just pretend that we have a aligned magnetic field with the spin axis of the star. And let's look at the magnetic dipole moment that we expect from that. So that magnetic dipole moment, m, is given by 4 pi over 15 times rho sub q times a radius to the 5th power times the angular velocity vector omega. And the B field at the North Pole B pole is given by mu naught over 2 pi times this magnetic moment over the radius of the star cubed. We're going to assume that model still holds after we shrink it down and we spin it up. Note that with these assumptions, what you get for this, the total Q of this rotating subset of the sun, that Q is in the ballpark of 6 times 10 to the 17 coulombs, which is in the ballpark of 4 times 10 to the 36 electrons out of a total of about 10 to the 57. So it's a very tiny fraction of the electrons in the sun required to produce that kind of magnetic field. Okay, so let's do this shrinking exercise. Let's take the star as it is now and somehow compress it down to a radius of 10 kilometers and ask what happens to that magnetic field. So once again, we shrink the sun to r equals 10 kilometers. And for simplicity, let's assume that Q remains fixed in that process. And what we find, and you're going to fill in the details in an exercise, is that the ratio of the new magnetic field to the old magnetic field is of order the old radius over the new radius squared. Or excuse me, not squared, cubed, excuse me. And so that means that our new magnetic field is on the order of 10 to the 14 Gauss. Okay, that's our sun. Again, the nearest star to us, come an arbitrary choice. What would happen if we shrunk it down? Well, the magnetic field would get really, really big. This would really qualify it to be what's known as a magnetar, something I'll talk a bit about tomorrow. An extremely high field star. And so just from this simple thought experiment, one can see it's not crazy to expect very high fields when you shrink a star. Despite the crudeness of that model, it's nonetheless suggestive that we can expect neutron stars to have very high magnetic fields. Now you might wonder at this point how much energy is associated with those high magnetic fields. Is it a significant fraction of the total mass energy of the star? Let's try to address that. So the field energy, I'll call U sub B, is 1 over 2 mu naught times B squared, square of the field, integrated over all of space, inside the sun and outside the sun. Inside the star, we have B is in the ballpark of the pole field. It's not quite accurate, but it ought to be in the right ballpark. Let's pretend that the magnetic field inside the sun is uniform and has a value that it has at the pole. And so the magnetic energy inside the star then is in the ballpark of 1 over 2 mu naught times this square of the B pole field times the volume of the star, 4 pi over 3 times r cubed. And then we can do the same sort of a calculation outside the star. And there we have the same kind of a calculation. Used to be outside is of order, an integral from r out to infinity of 1 over 2 mu naught. And then we have putting in the pole field as a benchmark and then rescaling according to that outside of the radius of the star. I'm going to suppress that by a factor of capital R over small r cubed, and then I'm squaring that so I get a 6th power of 1 over r. So of course the energy falls off very rapidly as we get away from the star. We still have to put in our Jacobian, and in this very simple calculation I'm ignoring angular dependence. You'll do this calculation without ignoring angular dependence and using a more realistic model for the inside field. But just for a order of magnitude result, what we end up with 1 over 2 mu naught B pole squared, radius lower limit, infinity for the upper limit, capital R to the 6th over R to the 4th dr. And so we end up with 1 over 2 mu naught B pole squared. And we end up with the same result as before, 4 pi 3 times r cubed. So we end up with pretty much the same result inside and outside of the star for that contribution. Again, this isn't quite right, but suggests that if we do it more rigorously, we're still going to get something in the same ballpark, which you should find. If you add them together, the total magnetic field energy is of order 6 times 10 to the 47 ergs times whatever the B-pole field is over 10 to the 15 Gauss squared times r over 12 kilometers cubed. So 6 times 10 to the 47 ergs is a lot. That's a big energy, but let's compare it to other relevant energies. So the mass energy of the star is basically 1.4 solar masses times c squared. That comes out to be 2.5 times 10 to the 54 ergs. So as big as this is for the magnetic energy, it's very small compared to the mass energy of the star, which isn't too surprising. We can also compare it to the rotational kinetic energy, another natural benchmark to compare against. And so there, our rotational energy is of order of 1/2 moment of inertia, I times omega squared. And again, using this very simple model of 2/5 mr squared for the moment of inertia, we end up with something that is 2 times 10 to the 53 ergs times the mass over 1.4 solar masses, radius over 12 kilometers squared, and F over 1,000 hertz. So this is a fast spinning star. Something is actually above what is probably the actual shedding limit. And so this is an energy that's not so much smaller than the rest mass energy, but still much larger than the magnetic energy, even for a magnetar with a field of 10 to the 15 Gauss. And so we conclude that the B energy is small with respect to the dominant terms. And we'll use that a bit later in the week. We're trying to assess the importance of magnetic field energy for gravitational wave emission. One point to be aware of, and I'll talk more about this quantitatively tomorrow, is that the field of older stars is much less than the field of younger stars. So for some reason, as stars age, and here we're talking millions, tens of millions, hundreds of millions, billions of years, the fields get weaker. And the natural question is, why is that? Well, one possible solution is that magnetic dipole radiation, which is, of course, robbing the star of energy, is something we're going to talk about more quantitatively tomorrow. That process depletes rotational energy, clearly, but it may also at the same time be reducing the dynamo associated with that same rotation. Again, we don't really understand how this works in detail, but it's plausible that that contributes. Another possibility, which I alluded to earlier, is ohmic dissipation. It's not clear how important ohmic dissipation is for this nominally superconducting and superfluid internal star, but that nuclear pasta diagram I showed you earlier is one possible place where you could get some significant dissipation from all that disorder. Okay, so we just don't know. That could be quite weak or maybe important. Another possibility is that the field can get buried. There can be burial of the infall of accretion from when the star is first formed. The aftermath can bring material down, plasma down onto the star. Or a case that's perhaps more relevant would be in a binary system where there is ongoing sustained accretion, and that accretion is, in some sense, a rain of plasma coming down on the star, and it's thought that that can drag the field inside the crust of the star. That said, as plausible as it is that you can bury the field, it's also quite plausible that it won't stay buried all that long. I'll close with that note that this buried field is expected eventually to reemerge. And so it's not necessarily a good way to go to explain billion-year-old stars' low magnetic fields based on the fact that the fields got buried at some point in the past. More likely that the fields just got weakened from another mechanism. That's a good place to stop for today. Let me ask if there are any questions. We're doing on time. Oh, actually I finished. Yeah. I'm sorry, I'm having trouble.
Can you elaborate more about the axion? Are you going to elaborate that later or just for the? I would like to know more about the axion, in which region is this formed, like in which region is this related?
There's one word you're saying I'm not quite catching, and it's a key one, I think.
I would like to know.
Oh, the shedding frequency, yes. So your question is, there's an exercise where you'll work through in one particular model, kind of an arbitrary model, what the shedding frequency could be. And again, we don't know precisely what it is. It depends on the equation of state. The shedding frequencies that I quoted earlier for a particular assumed equation state that's thought to be somewhere in the realm of reality. But we don't know what the right equation state is. And I'm not going to talk much more about that this week. I just want to give you a sense that we have a maximum of 716 hertz observed. We think the maximum ought to be higher than that by a significant amount, several tens of percent at least. And yet we seem to have a pretty hard speed limit. And I'll talk more later in the week about what that may be telling us. And hopefully it's telling us that gravitational wave emission is causing that speed limit, but there may be other causes too. Other questions? I'm not an expert on this at all, but my intuitive understanding is that as you have this plasma raining down, it drags the magnetic field with it. It's very much like what happens in our own Earth's magnetosphere and in the vicinity of the sun. You have in this case, an analogy to solar wind, and it will drag a field with it. And if it drags it inside the crust and the accretion is sustained, it may take a while for that field to reemerge. That's a nominal model. But I've never done the calculation myself, anything like the level of detail to convince myself that really makes sense. But people I respect have done that calculation, and they say it is plausible. Other questions? Okay. Thank you. Thank you.